Okay, we are starting with analysis of algorithms. The reason is the first part is on data structures. The second part is on algorithms. And both require analysis of the data structures or algorithms with respect to time and space. We want to analyze how much time a data structure takes or an algorithm takes, right? Similarly, space occupied by an algorithm or data structure, right? So as analysis is spilled throughout this course, we want to first understand how to analyze, right, algorithms. Okay, so you can call this algorithm analysis or complexity analysis or asymptotic analysis. They are kind of same. Okay, so the topics we will cover in this right section, right? Complexity analysis, worst case, best case, average case, asymptotic notations. Okay, let's start. So what exactly is complexity analysis? Think about a computer program. Suppose you have a computer program, you want to analyze the resources that computer program takes. And those resources can be time, space, maybe number of queries or number of messages transferred or number of processors it is using and so on. I mean, you can define hundreds of these kinds of resources, right? Okay, so how do you compare one algorithm you have written X and executed on computer A with another algorithm or another computer program Y that your friend wrote that was executed on a computer B? See, you have two programs X and Y, and they are run on A and B. And computers have different types of memory resources, such as processors and all those things. How do you even compare? Can you just take the runtime? So if you just take the runtime, you won't get the proper results because the performance, right? The practical performance or runtime depends on the algorithm itself, the computer on which it is run. That means the space, the RAM size, number of processors, and so on, right? It depends on the programming language. It depends on libraries. It depends on compiler, right? So on. How do you even compare your two programs, X and Y? So practical performance comparison is not the best way, though in papers we also give practical performance comparison, but the best way to compare is some kind of abstract model in which we can do a fair comparison. Okay, so in this abstract model or framework, right, we consider the total number of computations, asymptotic number of computations, or order of the number of computations, or messages, or queries, or something like that, right? This abstract model in which we compare two computer programs, you can say complexity analysis, right? So here we don't give something like this computer program takes 7.8 seconds. It is meaningless, right? We just give the order of this complexity. For example, theta of n squared, theta of n log n, O of n power log 3, so on, right? And this framework is complexity analysis. And you want to understand how, right, we do this. And whatever we discuss here is applicable for time, is applicable for space, is applicable for number of queries, number of messages transferred, so on. So this framework is independent of what you are applying to, right? Time, space, and other resources, right? So this is a beautiful abstract mathematical, right, model we use. Okay, so as we already discussed, the running time of a computer program depends on the algorithm itself. If there are 10 different algorithms to solve the problem, the same problem. I mean, you want to choose, you want to fix your problem, right? Okay. So fixing your problem, there can be 10, 20 different algorithms to solve the same problem. The runtime varies based on the algorithm. For the same algorithm, if you have two different input sizes, again, the runtime for the same algorithm will vary depending on input size. So larger input sizes might take a lot more time, right? Similarly. So for the same input size, it depends on the data distribution. Suppose the input size is, say, 100 elements, right? So suppose the input itself is an array. The input size is 100 elements in that array. Depending on how the data is distributed, the runtime can vary. The runtime can vary based on the machine or the computing system. For example, if you run the same program on a 1950 machine and today's machines, you see the difference, right? Okay, so that's machine. Next, operating system. Again, some operating systems have native calls for many arithmetic operations and all those things, right? So depending on operating system, the runtime can vary. Depending on the compiler, it can vary. Compiler will have optimization, its own algorithms, how to consider instructions and all. Programming language, and you know this very well, right? In higher level languages, Python is the slowest programming language. Next is the much better would be Java. Much better than Java is C++. So much better than C++ is C in terms of speed, right? So depending on which programming language, again, the runtime can be. Coding, right? The way you have coded, right? So all these things. Anyway, so now we will just do not care about all these other parameters like machine, operating system, compiler, programming language, coding, anything. We will just focus on the algorithm, the input size of it, and input data distribution. That's it, nothing else, right? No other parameters. So this we call asymptotic analysis or complexity analysis in general. Right? Okay, so as we said earlier, we give this complexity for different resources. Time complexity is, say, O of n squared. Space complexity is, say, theta of n. Cache complexity in the sense number of cache misses. In operating system, this can mean the number of IO transfers or page faults, right? Okay, so suppose it is O of n squared divided by Bm. So we have some other parameters like Bm. What is B? What is M? Suppose this is your RAM and this is your hard disk. Whenever you bring data from hard disk to RAM, it is brought in terms of block size B. I mean, you cannot get 1 byte only. You get a block of data, right? B units of data. Okay. Next, suppose this is the RAM size M. Then the total number of message transfers will be this. That is the cache complexity. The total number of these block transfers, right? Or it is also called IO transfers. It is also called page faults, right? So it is n squared by Bm for some algorithm. And suppose you have another problem where the query complexity, the number of queries, the number of questions asked.
Professor.
Yes.
Why it's n squared divided by Bm?
No, I mean, so I have just considered some random examples here.
Oh, okay, I see. Okay,
right?
never mind.
Just some random examples.
Okay.
How we consider complexity analysis. Query complexity is, say, omega of n log n and O of. So what is the meaning of O? What is the meaning of theta? What is the meaning of omega? Right? And why do we have two complexities here? Omega as well as O. What do they mean? Right? And there are more notations, small o, small omega. So we want to understand these notations and why we consider the complexities or say runtime or space or right? For all these parameters in terms of these, right? We want to understand. So that is this complexity analysis or asymptotic analysis, right? Or analysis of algorithms. See, here we are not giving, this is 4.5 seconds. We are not saying space consumption is 27 MB of RAM. No, it's not like that. Okay, cache complex, we are not saying that it is 1 million page faults. No, all these numbers are useless, because if you go to another machine, all these numbers change, right? Hence, we are using a mathematical framework to analyze performance. Okay, so that is asymptotic analysis. Okay. Next. So here are some examples, right? So consider all these problems. There are so many, you don't need to understand each and every problem here. So we have some algorithms for a couple of problems whose running time is bounded by a polynomial, right? Bounded, at most it's a polynomial, right? See, even log n is not a polynomial, but it is bounded by a polynomial. Log n is less than n asymptotically, right? We will define what is this order of group and all that. And why do we have this O? We will define it later, right? Just get the feel of all these things. Okay. Next, we have a couple of problems where the best algorithms we know of take exponential time. That means, is there a proof that there are no polynomial time algorithms to solve these problems? No, we don't have a proof. The current best algorithms to solve these problems take exponential time. Nobody knows about a polynomial time algorithm for these problems. Okay, if time permits in the course, we will also look at something called NP problems, right? NP or NP complete problems. NP complete problems. That means the current best algorithms are they take exponential time. Nobody knows about any polynomial time algorithm for these. Okay, next, there are a couple of problems that take infinite time for some problem instances. Not all instances. There is at least one problem instance for which the runtime is infinity. Okay. Okay, think about it for a minute. That means if there is one problem instance for which the program does not stop, does not halt, does not terminate. So what do we call that? There is no solution. There is no solution. That means, what is a solution, or what is an algorithm that takes, I think we defined it in the previous session, right? Step-by-step procedure that takes finite number of instructions, or that solves the problem in finite amount of time. This does not solve the problem in finite amount of time. So these problems are algorithmically impossible. Impossible. Right? Unsolvable. Impossible. That means, consider this. Program correctness. That means you can never develop a software. Never ever develop a software, even if you bring in all best software engineers in the world, right? That can take another computer program as input and give yes or no as the output. Yes, if the program is correct, input program is correct. No, if the input program is incorrect. You cannot develop such a software or algorithm. Why? Because there are some input for which that software takes infinite amount of time, right? So similarly, halting problem. So you can think of this as an app, Android or iOS app, that checks whether another app crashes on your iPhone or not, right? See, you face all these problems on Windows and even on iOS, right? Hanging. But of course, the amount of these hanging or crashing can vary, but you have this problem, right? Crashing or hanging. That means, when do you say that a program has crashed or a program is hung? If it takes infinite amount of time, it never stops, never terminates, right? So you cannot write a software that checks whether another app crashes or not, right? So these are algorithmically impossible. Anyway, we will not cover this part, right? But we will just analyze all these problems that take finite amount of time. That means problems for which algorithms exist, right? And we compare the runtime complexity or space complexity and something like that. Okay, we will not focus on all these problems here. Next. As you saw earlier, different algorithms have different complexities. I mean, some can have the same complexities, but you see a lot of examples, right? And these complexities are mathematical functions, right? So you saw there was an algorithm that took log n time, O of log n, I should say O of log n, or O of root n time, or say theta of n time, and so on. All these are mathematical functions that you have learned in your school. Let's compare them. So you see that n factorial and 2 power n are the slowest functions here, right? Slowest in the sense they take a lot of time, even for small input. See, this is the input size. When you go here, when n is increased, that means input size is increasing. This is the time taken. F can be the time taken, or it can be the space complexity, or it can be the number of queries, whatever, right? You can define it in, I mean, based on the algorithm you're working on. See, this means that for a small amount of data, it takes a lot of time. So these are kind of bad functions. So if there are algorithms which take this much time, they are called slow algorithms, right? Exponential time. All this is exponential, n factorial, 2 power n, n power n, all these. And all these are bounded by polynomial functions. So they are depicted here in blue. We call them as fast functions, right? Fast algorithms or fast functions. Even if it takes n power 10, I mean, we consider it as fast. The reason is we should have a boundary, right? We have the boundary here. All exponential time algorithms are slow. All functions that are bounded by polynomial time are fast. Okay. Okay, so what do you consider here when you are considering the runtime? So you consider the most basic operations. What are the operations here? There are different types of operations. There can be arithmetic operations. There can be comparison operations. There can be memory operations, right? Function invocation, the calls itself, you can call it as an operation, or there can be bitwise operations, and so on. I mean, there are so many types of operations, right? Okay, so consider this: multiplication, division, plus, minus, all these are arithmetic operations. So you can consider those as taking 1 unit of time for simplicity. Let's also consider these comparison operations. Let's also consider these take 1 unit of time. And what about assignment? This means assignment. B value, the value of B is assigned to variable A, right? And what about C of I? C of I. So it has to do this offset, right? Find the offset I and plus the base pointer. So it has to do all these operations, right? So let's also consider each of these operations as taking 1 unit. So you want to find the total number of operations, right? Okay. And then we will define the order of growth for those operations. Let's take a simple example, array sum. You are given an array of n numbers and you want to add all the values. Okay. So array from 0 to n minus 1, sum is equal to 0, and this is a very simple program. Let's directly go to the operations. So we have one assignment here, one operation. And what do we have here in line 2? So we have comparison operation. See, every time it compares whether it is less than or equal to n minus 1 or not. So that is a comparison operator. And then an increment operator, I is equal to I plus 1, right? So that is the increment operator. So you can see there are 2n operations here for line 2, right? For each value, considering each value of I, incrementing, comparison, everything. And next you have line 3. In line 3, what do you have? Sum is equal to sum plus a of I. So you have one assignment here, you have one add operation here, and you have one indexing operation here. So you can consider as it is inside the for loop 3n operations, total of 3n operations, and return sum. Okay, let's say one operation, accessing it or returning, whatever. Now, so if you add all these things, what do you get? Maybe say 5n plus 2 operations, and you can write it as n comparisons, n increments, n memory index accesses, and so on. But the problem is, this is for a simple 4-line program. What if you have a 1 million lines of code, right? Finding all these things and comparing will not be fruitful. And what if you have, say, n1 comparisons, n2 increments, n3 memory indices, so on. So which one do you take here, right? Okay. So instead of finding the exact number, we will use the order of growth. Okay. And we will define it later. Okay. Before we look at order of growth, we should also look at the different cases: worst case, best case, average case analysis. What is the meaning of this? Worst case, best case, average case. You know that the runtime of an algorithm, here we will focus on runtime throughout, but this idea can be applied to space complexity, query complexity, cache complexity, so on, right? But from here on, we will majorly focus on time. I will just say time, runtime, running time, performance, right? So on. But all this analysis will be applicable for other resources also. Okay. Now let's focus on this runtime, T. So T of n, that means n is the input size, right? You have, you're inputting n elements or n numbers, n strings, something like that. Okay. But for the same input size, the runtime can vary. We will see an example soon. Okay, why will it vary? So as we discussed earlier, the runtime also depends on data distribution. What if the n elements are already, completely sorted or it in the right format? You don't need to do any processing, right? That is a good data distribution. What if the data distribution is so horrible that you want to order all the elements in a properly ordered fashion, arrange it, and that takes a lot of time. So here the data distribution for the same n elements can affect the runtime. Hence we define worst case, best case, average case analysis. Okay, let's see. What is worst case? T worst of n. That means given size n, the worst case complexity is the running time for the worst case input of size n. So as we discussed earlier, for the same size n, okay, let's say this is scenario 1, 2, 3. Suppose there are 1 million scenarios like this for the same input size n, right? And time taken for this is say T1, T2, T3, so on, T1 million. See, maybe this T3 is the maximum of all these T1 to T1 million, right? That means this data is so horrible that the processing of this data takes a lot of time. Then this is the worst case input, and this is the worst case complexity, right? That's the meaning of this complexity for the worst case input. Okay, similarly, you can define complexity for the best case input. The arrangement of data might be so that the time taken is the fastest, then it is the best case input. Okay, what about average case input? So you want to consider a random input, one out of these 1 million, and check what is the expected value of this complexity T expected, right? That is like the average case analysis. So you can also call this as T expected case complexity, something like that for random input. That's what you do with, in the theory of probability, right? So when you toss a coin or throw a dice, what is the expected number you get on the dice? What do you do there? You think about all the probabilities and the numbers that you're going to get and take the average of it, right? The same idea is used here. Whatever you used in the theory of probability is this average case complexity, considering all types of input, what is the probability of occurrence of those kinds, and then taking the average, weighted average of all those. Okay, that's the average case complexity. And sometimes average case is important. Okay, next, amortized complexity. What is amortized complexity? So suppose there is a data structure. Let me erase this. Suppose there is a data structure and you did one call here, say call to an API here, another call to an API, another call to an API, so on. API or just the function, okay? And this call took some time. This call took some other time, right? Some other time, so on, TK, some other time. Okay, now what is the amortized complexity? See, maybe it took, say, constant time here in T1, T2 maybe took the order of n and something like that. But you have to call all these functions or all these operations or something like that. Then what you do is you take the sum of all these things and take the average, right? And take the average of all these things, see, divided by n. That is the amortized complexity, right? That is amortized complexity. See, this amortized complexity is very different from average case complexity. How? See, this is not considering all types of input of the same size. No, it is considering the operations that the algorithm is calling, and it doesn't want to look at one operation, hence it is the taking the average of all this. So this is different from this one. So probably we will understand more about amortized complexity when we look at arrays. Okay, so till then, hold on.
Professor?
Yes.
For the amortized complexity example, shouldn't it be divided by k for all the time?
Oh, yes. Sorry. Yes, it was k, not n. Okay. The amount of the number of operations you did. Right? True. Okay, that was a simple example. We will look at a proper example in this arrays. When we look at dynamic arrays, we will encounter this amortized complexity and we will understand it in a better way, right? So without examples, it will be slightly complicated to explain. But right now, you just need to know worst case, best case, average case. Now, you should ask one question. Given n, what am I computing? By default, when someone says compute the complexity, by default, implicitly, they mean worst case complexity, right? Because when you create a software and say your clients or customers are accessing it, they don't care about best case. That's unimportant to them. What is important to them is the worst case. Worst case, how much time a customer has to wait until their problem, say they are clicking on something which is running an operation, or they are doing some of these operations, right? What is the worst case time they need to wait, right? So when they are solving a problem, right, it might be clicking a button or something like that, right? Worst case complexity is the default complexity. Whenever someone says, what's the running time, you need to compute the worst case complexity. But if someone explicitly asks, find the average case complexity, then find the average case. Okay, so what is the worst case, best case, average case analysis or complexity for this searching? Suppose you have an array, n numbers are there, right? You are searching for an element key. I won't go over this pseudocode. This is very simple. I is equal to 0 while I is less than n. E of I not equal to key. I is equal to I plus 1. If I is less than n, return that position. Else return -1. -1 means that there is no value key in the array, or any other index means that there is a value. Okay. This is a simple, straightforward, linear searching algorithm. Now let's look at worst case, best case, average case, everything. What is the worst case? The worst case is when the element is not found. Suppose the element is not found, you need to scan all the elements, right? You will do, in the worst case, n comparisons, right? So your worst case is n. What is your best case? The best case is the element you are searching for is in the first position. That's your best case. Okay, what is the average case? Now let's consider this. If search is successful, it's n plus 1 by 2. If search is unsuccessful, it is n. Suppose P is the probability of successful search. Okay, what is the average case? See, P is the success probability and 1 minus P is the failure probability. The search fails with 1 minus P, failure probability, and the total number of comparisons required is n. Okay, success probability is P, but there are n positions. So you assume that the element is equally likely at every position. So you divide P by n everywhere. If the element is at the first position, the number of comparisons is just 1. If the element is at second position, the number of comparisons required is 2, right? So on. If the element is at the last position, the number of comparisons required is n, right? When you take the average of all this, what do you get? This is the final expression. That means with the success probability of P, what is the total number of comparisons? N plus 1 by 2. With a probability of 1 minus P, right? So if search is unsuccessful, the number of comparisons is n. This is your average case analysis. Got it? So what is important here? we majorly care for the worst case, right? N plus 1 by 2 is almost half of the array, right? On an average, you search for half of the array if the search is successful. If the search is unsuccessful, definitely you will scan N. Got it? See, this is the analysis behind a worst case, best case, average case. And by default, you should always find out the worst case. Asymptotic notations. Okay, let's start with these asymptotic notations. First, let's define a term here, asymptotically positive. What is the meaning of asymptotically positive? So whenever I use T of n, assume that T of n is the runtime function of an algorithm or a computer program. Okay, so T of n is asymptotically positive. We will assume that from now on, every function we touch is asymptotically positive. Why is this required? Okay, so before we look at the motivation and everything, let's define it. What is asymptotically positive? T of n is a function from r plus to r such that for all n naught, there exists n naught such that for all n greater than or equal to n naught, T of n is greater than 0. What does this mean? See, T of n is a function, right? It's a function. It is defined for all positive reals. So if you have a number line, see, oh, this is positive reals from here, so on up to infinity. It is defined for this, and the output is a real number. The output is a real number such that there exists n naught, right? There exists n naught for all n greater than or equal to n naught. For all these values, T of n is, say, positive. It should always be greater than this line, right? So this is your T of n for n greater than or equal to n naught. T of n is positive. That's the meaning of asymptotically positive. See, this is positive. It cannot go below x-axis. This is your n is the problem size, x-axis, y-axis is the either it is runtime or space complexity, whatever. See, number of computations, T of n is asymptotically positive. Space is asymptotically positive. Cache misses is asymptotically positive. Number of queries is asymptotically positive. Why? Because when we deal with positive functions, we can define order and all those things. If the function keeps, if it goes to axis below here, right? Below this x-axis, it will be difficult to compare which is greater, which is smaller, and so on. Hence, we assume that everything is positive after some point, n naught. Why we don't care about this from 1 onwards? It doesn't matter. So we always look at infinity. After at infinity, what happens? That eventually, right? When the input size keeps getting larger and larger, what happens? Eventually, what happens? Hence, we don't care about, it has to start from 1. It can start from any n naught. Okay, so here on, every function we touch, we will consider that as asymptotically positive. So you cannot have something like this, right? You will never ever use a function like this. Why? When n increases, this is decreasing, and this is not asymptotically positive. This one, right? Okay, so this is the definition of asymptotic notations, right? Using set notation. Okay, what are these notations? See, theta of g of n, O of g of n, omega of g of n, small o of g of n, small omega of g of n. So this is called big O. This is called theta, big theta, or this is called small o. This is called small omega, and this is called theta. Oh, I made a mistake. This is omega, sorry. This is omega, this is theta. Or big theta. You can call this as big theta, big O, big omega, small o, small omega. Okay. What are these actually? These are sets. All these are sets, right? These are collections of functions, sets of functions. In fact, it is an infinite set. That means there is an infinity of functions in this set or bucket, right? This is a box of functions. This is a collection of functions. Okay. But they have to satisfy some properties. It is a collection of all functions f of n such that, now let's look at theta definition first. Theta, such that f of n is between constant times g of n and another constant times g of n. Simple, right? F of n is between constant times g of n and another constant times g of n. And of course, both will be greater than or equal to 0 because we have defined that asymptotically positive, all those things, right? Okay. It has to be between constant times g of n and another constant times g of n such that these two constants are positive. These two constants are positive, and this is true for all n. That means all n greater than or equal to n naught. That means eventually, when someone says for all n greater than or equal to n naught, I mean there exists n naught such that for all n greater than or equal to n naught, the simple meaning of this is eventually. Eventually, right? It's same as eventually. Eventually, this function f of n will be between g of n multiplied by constants. That's the meaning of theta. Okay. What about O? Okay. Before that, what is the meaning of this? F of n between the same function. F of n is upper bounded by constant times g of n. F of n is lower bounded by constant times g of n. That means f of n has the same order of growth as g of n, same order of growth. We will define the other notations later, right? Same order of growth. Okay, what is O? F of n has a smaller order of growth than g of n. I mean, smaller or equal to, right? Smaller or equal to order of growth than g of n. So that's the meaning of O of g of n. So f of n is at most g of n. You can say f of n is at most g of n. F of n is less than or equal to c times g of n, such that c is positive everywhere. All these constants are positive, right? There exists n naught. N naught is positive. And for all n, it should be greater than or equal to n naught. That means eventually this function is upper bounded by g of n, right? So what is omega? Big omega function f of n is lower bounded by g of n, right? F of n is lower bounded by g of n. What is small o? F of n is strictly less than g of n. That means strictly less. That means it has smaller order of growth than G of n. It can never equal G of n. Here, what is the difference between big O and small o? Here it can equal, but here it can never equal. The order of growth or the rate of growth of f of n eventually will still be lesser than that of G of n. That's the meaning of small o. Similarly, small omega, f of n has a larger rate of growth, faster rate of growth than G of n. Got it? Any questions here?
Excuse me, in your case, function n will be small o of 2n, right?
So n is equal to?
N is small o of 2n by your definition.
Small o of 2n, or why?
Yeah. Because if we take c equals 2, it will be smaller for all n starting from some point.
Okay, so let's apply the definition. F of n, so you're saying f of n is equal to n, G of n is equal to 2n, right?
Yeah, right.
Okay. And there exists n naught. Okay, let's also define this. F of n, f of 2n, c times, okay, there exists c greater than 0. That means c is equal to 2 here, right?
Right.
F of n less than 2 times n. Let's see.
Yeah, so for all n greater than 0, it satisfies this condition, right?
Yeah, I also think it should be for all n.
Yeah,
Yeah,
so
so
like for all n greater than 0, it satisfies this. Then we can say like, for small o of gn, this condition satisfies, where f of n is less than c times g of n.
I think this is valid.
I
It
see.
satisfies the small o.
Right. Okay, so I will check these definitions again, right? Small o and omega. That's a very good question. If we just take the constants.
I actually believe it should be for all c greater than 0. Then it should.
There exists or for all c. For all, I think it is there exists only. But anyway, so I will check this, right? Whether the mistake is it here or n naught. Okay, so this is a wonderful question. So can you email me the question so that I can exactly know who asked it?
Yeah, sure.
Right. Okay, so I will verify this. This is a fantastic question. Thanks for pointing this out. And we have another definition, right? We will also apply another definition and check, right?
Yeah, I think I just Googled quickly. I think it's I forgot who said that is correct. So here should be given any n larger than n0, you can constantly have any c as long as c is larger than 0. This less than gn should hold.
Okay, so this is for all.
Yeah, I think so. Yeah.
Yeah. So if this is the culprit, let's see, for all. There exists. Okay, then probably everything, all these things should change, right?
Yeah. So the difference here is for big O is at least one C. For small o is any c as long as they are positive.
Okay, so yeah,
I think that's
okay,
close.
that's a wonderful point. So I will check this, right? The
Okay.
condition, it's majorly the C problem. The problem with this constant, right? C,
Yeah.
whether it is there exists or it is for all,
Yeah.
whether it is greater than 1 or whether it is greater than 0, right? These are majorly the problem points.
Yeah.
Yes, you're right. I think it is for all, but whether it is greater than or equal to 1 or 0, so I will check this.
I
Very good point.
personally I think 0 or 1 is not important as long as it's a constant. 0, 1 can always be normalized.
Right. So I think 0 should be greater than 0 should be fine. I don't see a problem here, but so we will check if there are any corner cases, right? But yes, I think it should be for all. So this was the mistake. There exists, right? Okay, very good. So please email me, right, about this bug. Thank you so much. Very good.
But here the C can be anything between 0 and 0.5, considering the same example, and then f of n would be greater than C into G of n, right?
No, I mean, if it is C greater than 0 for arbitrary value of C greater than 0.
Yeah, so if it is something like 0.00001, then f of n would be greater than C of G of n in our example, right?
Then it won't work because G of n is 2 times n, right?
Yeah,
when
so
you multiply by C, it will be smaller than f of n.
We can't say for all C greater than 0 then.
No. In the definition, if it is there, then the count that will be a counter example. Right? If in the definition, if it is for all, so we know that n is not small o of 2n. We know that for sure. Right? Then there should be a problem with this definition. I think the fix should be this, the way C is defined. Right? If we define C in this way for all C greater than 0, then that fixes the problem. Okay?
But that, I don't think that does fix the problem. I think that creates the problem.
Yeah, if we put it for all C greater than 0, then we're also including 0.0001 as the possible C value.
Oh, so how? Yeah, so if it is 0.0001 times 2 times n, f of n
will be greater in our example.
So which one? If C is equal to
0.0001. Yeah.
Okay, so here it is true, but
Excuse me.
if C, I mean, if when you replace it with for all, right? If you replace it with for all, this statement will be wrong then.
Yes.
Right? That statement will be incorrect. F of n is not O of 2n. Say f of n is equal to n. N is not O of 2n. Because when C is chosen as 1 million, wait a minute, when C is chosen as 1 million, okay, wait a minute, if this is true, this is if C is small, it violates the condition, right?
Yeah, if the definition of C is for all C greater than 0.
Right. If it violates the condition, then n is not equal to small o of 2n, right? And that's exactly what we want.
Here, I think the small o gn in comparison to fn is basically to say that fn decreases faster than gn. So if you have the constant like 1n, 2n, 3n, whatsoever, I don't think it satisfies. However, n will n square, n will be o n square, smaller o n square. So when the n goes to infinity, n square increased faster than n. So that becomes 1 over n. When 1 over n, when n goes to infinity, 1 over n goes to 0. I think that's basically the point of the smaller gn.
Right. So it's majorly through this constant. So I will check this again, right? For which values, I think it might be 0 here. Probably it is not greater than 1 anywhere. But I think this should be changed to for all. That should fix the problem, right? Okay, and we will define these things using limits. You will also see that definition.
Yeah,
Okay?
that's probably more
will be
strict mathematical.
Easier to see, and it cancels the effect of all these constants. Okay, now let's look at the definition of these asymptotic notations using limits. Okay, now see here. Limit of f of n divided by g of n when n tends to infinity. If you get it as 0, then it is equivalent to saying f of n is small o of g of n. Right?
Yeah, exactly. Yes.
Yes.
Is this correct?
Yes.
Yeah.
So what happens to the problem you mentioned earlier then?
If in my example, right, the fn is n, gn is n squared, then when n goes to infinity, the limit is 0. But if you have 2n and 2n, then you got a constant. So
Right.
this is not satisfied.
So if you have n divided by 2n, what happens? You get
Just
1
a
by 2.
constant, yeah.
Right? So if you have limit n tending to infinity, this is greater than 0 and is and less than infinity, right? It's a constant. So it is not this. So this should cancel the effect of all constants, right? So
Yes.
I will fix the previous definition using sets, but this will be easier to see and analyze. So limit of n divided by n squared n to infinity is equal to limit of 1 by n tending to infinity is equal to 0. Therefore, n is in small o of n squared. So does this make sense?
Yes.
Okay, so what is small o? The meaning of small o is strictly smaller than, asymptotically smaller than. The rate of growth of f of n is asymptotically smaller than the rate of growth of g of n.
Yeah.
Okay. Next, f of n divided by g of n is equal to infinity is equivalent to f of n is omega of g of n. You can consider this as kind of opposites to each other, right? Kind of opposites. So suppose you write like this, n squared by n, limit n tending to infinity. What do you get? Limit of n tending to infinity is equal to infinity. Therefore, n squared is omega of n. That means strictly greater than, asymptotically greater than n. Okay. Next, suppose L is a finite number, right? Between 0 and definitely not infinity, right? A finite number greater than 0. And suppose limit of f of n divided by g of n tending to infinity is L. Then it implies that f of n is in theta of g of n. See, some people write this as equal to, okay, equal to. But you know, equal to is not the best way to represent it. Why? You know that f of n is one function, right? And all these notations is a set of infinite functions. So equal to is not technically right. So we have this belongs to or is present in the set notation, right? Let's use this because this is technically better, technically correct. Okay, so what is the meaning of this? If the limit exists and is equal to L, some constant greater than 0, then it is theta. They have the same order of growth. Look at these directions. This is one direction. It doesn't say that if f of n is in theta of g of n, it means the limit exists. So here is the counter example. See, if f of n has the same order of growth as g of n, however, the limit does not exist. Consider this n squared and 2 plus sine n squared. What happens? You know that it's theta of n squared, right? N squared is equal to, so can you show that f of n is equal to theta of g of n? How do you show that? How do you show this? How do you prove this given f of n and g of n?
It's upper bounded and lower bounded by 3 and 1.
Exactly.
Yeah.
You know that sine function is upper bounded by +1 and lower bounded by -1. So 2 plus 1 is 3. So this is less than or equal to 3n squared, greater than or equal to n squared, right? 2 minus 1. Hence, this function is theta of n squared. However, let's think about the limits. What happens when n tends to infinity? Here, n squared and n squared cancels. What happens to sine infinity?
It just jumps between 0 and 1
Exactly.
and -1.
It keeps oscillating between positive and negative. It's not defined. Limit
still
does
bounded.
not exist, right? Hence, the limit definition applies only one way. If the limit exists, then it is theta. If it is theta, it doesn't mean that the limit exists. Okay. And as you compare these two definitions, right, you see that limit definition is the easiest to solve problems.
So, Professor, can I just ask a quick question?
Yes.
So if the limit does not exist, we say that f of n is in theta of g of n?
If the limit does not exist, we don't know.
We don't know.
We don't know.
Okay,
Right?
thank you. Yeah, okay.
I mean, it can be theta, it might not be theta, we don't know. If the limit exists, only then we know for sure that it is theta. Okay, now let's see. Limit of t of n divided by g of n. T of n is your running time, right? So if you get 0, it means that t of n has a smaller order of growth than g of n. A constant c greater than 0, then it implies it has the same growth rate as g of n. Infinity means t of n has a larger growth rate than g of n. And as per previous slide, you know this already. So smaller growth rate means t of n is in small o of g of n. Same growth rate means is in theta of g of n and omega, small omega of g of n. Okay. Now, L'Hopital's rule. So L'Hopital, look at all these constraints. I will not go over all these constraints. See, sometimes whenever you want to compute limits, you can use this beautiful rule. It's also called Bernoulli's rule. So limit of f of x divided by g of x. Suppose it is of the form 0 by 0 or infinity by infinity. or minus infinity by minus infinity, something like this, right? When x tends to c. You don't know how to compute limits now, right? So what Bernoulli proposed is that in such case, if this limit x tending to c, f dash of x divided by g dash of x exists, and you know that g dash of x is not equal to 0, then this is same as limit of f dash of x divided by g dash of x. And what is f dash of x? It is differential of f of x with respect to x, right? Similarly, g dash can be defined. So this is a fantastic rule, and we use heavily when we want to compute limits. Okay, so here are some asymptotic notations. Let's define these notations. See, this means asymptotically equal for theta, right? Asymptotically equal, asymptotically less than is what? Which is this? Less than, small o,
Small.
less than or equal to o, greater than omega, and then greater than or equal to big omega. Okay, big omega, this omega. Make sense? Okay, so two functions we write like this: f of n is asymptotically equal to g of n if and only if f of n belongs to theta of g of n. So we write it as asymptotically less than or equal to g of n if it belongs to O of g of n. I mean, I like these notations. It is from Markov's book. It's a fantastic book on analysis of algorithms. Okay, let's use notations, these notations. Okay, so you understand this, right? So we have equal to, less than or equal to, greater than or equal to in arithmetic. Similarly, we have defined these 5 notations to compare the rate of growths of functions. So, you know, whenever we write f of n, you can assume this is a function. And whenever you write g of n, this is also a function. But whenever we are comparing this, we are comparing the classes of functions they belong to, right? Something like that. Okay, next. So you know these properties, right? Reflexivity, symmetry, transitivity. So these are the properties you study in relations. And these are relations. Now let's see which of these properties are satisfied by which notation. So equal to reflexivity. So what is the meaning of reflexivity? F is asymptotically equal to F. Okay. Symmetry, if F asymptotically equal to G, then G asymptotically equal to F. What about transitivity? If F equal to G, if G equal to say H, then F asymptotically equal to H. That is transitivity, right? So similarly, you can define many other relations like this. Go over this and try to prove them rigorously using the definitions, right? Try to use these definitions, the set definitions, the limit definitions, and try to prove, you know, all these properties. And there are many more, right? F of n is less than or equal to g of n, is same as g of n is greater than or equal to f of n. So here I call it as greater than or equal to, but assume that I'm saying asymptotically greater than or equal to. F of n is less than g of n, same as g of n greater than f of n. And what else? I mean, we will prove other properties. Okay. So try to prove all the properties given in the table using the definitions. So here are some examples. O of g of n. What is O of g of n? the class or set of all functions that have order of growth at most g of n. Similarly, omega, the set of all functions that have order of growth at least g of n. Theta, or class of functions that have the same order of growth as g of n. Okay, so go over these examples. Okay, next, so here are some diagrams. See, theta means that you have this function t of n. They are between constant times g of n eventually for all n greater than or equal to n naught. This is the case, right? It won't happen like this. It won't go beyond this or something. Okay, next. O means it is upper bounded by constant times g of n. Omega means it is lower bounded by constant times g of n. It can equal to also, I mean, it can be equal also. It need not be strictly greater than, right? See, another way to visualize all these notations is thinking about the classes themselves. See, this is a big set, theta of 1. Theta of 1 means constant, 10, 100, and we will define some other functions also. All these functions are in theta of 1. Theta of log n, log 2n, right? Log n power 100, 3 log n, all these are in this class. Now, can you tell me why is log n power 100 in this class?
So log
It's
n
just a
to the
constant
power.
times and log n.
100 times log n, right? That's the rule of logs. Okay, good. So similarly, you can define all these buckets or sets or classes of functions, and they are kind of distinct. What about omega? What about omega? So look at this, omega of n factorial. So omega of n factorial, what is the meaning of it? All functions that have at least n factorial are here, that have order of growth at least n factorial. And all functions that have order of growth at least 2 power n. That means omega of n factorial is a subset of omega of 2 power n. Omega of 2 power n is a subset of omega of n squared, and so on. So look at this subset relationship, right? Similarly, you can define infinite sets like this. So in the same way, you can also define, oh, I had another diagram. Oh, for O notation, O of 1 is present in O of log n, is present in O of root n, so on. Now, so a couple of, so what we will do is we will come to these problems later. Let me quickly go over these problems, because I have already released homework 1 on Blackboard. You might have got the notifications, right? So we will look at 2 types of problems majorly. First, I will start with this. Suppose you want to find the complexity of all these kernels. So what do you do here? Look at this. You have the loop kernel, and you just have 2 loops. For I is equal to I start, I less than I end, I increment, j is equal to j start, j less than j end, j increment, do nothing. What is the number of basic operations? See, you still do this comparison in the for loop, right? Assume that you're computing the total number of comparisons asymptotically, right? You don't want the exact number. You want to find the asymptotic function of the number of comparisons. And here are 20 different kernels given to you. See, 20 different kernels. What if I start is 2? What if I start is n? And I increment is this, j start, j and j increment. This is one loop, looping kernel. This is another looping kernel. So on, you have 20 looping kernels. So how do you solve this problem? Suppose our looping kernel is this, right? I start from 2 to n, increments in additions of 2, right? J is equal to 2 to n, increment in additions of 2. Now look at this carefully. So what are the values taken by I takes 2, I takes 4, 2 plus 2, right? 4 plus 2, 6 plus 2, 8. So on up till it should be less than n. So what is the number less than n, but it's a multiple of 2? It is this, 2 times floor of n by 2. So I takes all these values. For every value I takes, you have another sigma, right? J takes all these values, second loop. See, J takes 2, J takes 4, exact same logic, 6, so on up till 2 n by 2. And in the inside of the 2 loops, you do nothing, but you are still doing comparisons, right? Assume that this is one comparison. One means you're doing, say, one comparison. Even that do nothing is a semicolon, that means you're not doing there, but you have to compare, right? And add, increment, all these things. So consider this as one comparison. Now, how do you solve this? See, I and j are kind of independent. There is no dependency. Hence, sigma of I, sigma of j can be considered as sigma of I times sigma of j, because these 2 loops are completely independent. Okay, so how many values are there here for j? See, exactly, there are n by 2. So this would be called n by 2 times, this will be called n by 2 times, multiply its theta of n squared. Make sense? So this is how you compute the complexity of a kernel. Similarly, what about j is equal to j times 2? So the idea is you start with 2, I loop remains the same. Now only j loop is changing, right? Because of this increment, j is equal to j times 2. So you start with 2 and multiply that with 2, 2 power 1, 2 power 2. Multiply that with 2, 2 power 3. So on up till a power of 2 less than n. You can say it is something like this, 2 power log n. 2 power log n. I mean, though we wrote it as less than, but this can be equal to n, right? It's okay. I mean, just one value is fine. It's not a big deal, right? Okay, so 2 power floor of log n. Again, these 2 are independent summations, so you can split them. Now, how many terms are there here? Log n. So n by 2 times log n, n log n. Right? Next, the third kernel. J is equal to j squared. So what happens here? See, initially it is 2. This is 2. And next time it is 2 times 2. 2 times 2 is 4. 4 times, sorry. 2 squared is 4. 4 squared is 16. 16 squared is 2. What is this? 16? Is it 216? Something like that.
256.
256. Okay, 256. Okay, now look at this. How does this grow?
That's 65536.
2 power 0, 2 power 2 power 1, 2 power 2 power 2, so on. Right? That's what is written here. So this is 2 power log of log n. Right? Again, split it into 2 components here. This is log n plus 1. Theta of n log n. So what I have showed here are the way of deriving the complexity. Okay, the way of deriving the complexities for these kernels, 3 kernels, right? So similarly, you can work on the other 17 kernels. Okay, so derive the complexities. This is your homework problem, and there is another problem. So you have a lot of functions like this, and you want to find the relationships between these functions. And why do we do this? Suppose you have computer programs which take different amount of time complexity wise. That means they represent different functions, asymptotic functions, and now you want to compare between two programs which is faster than the other. That then you need to use this asymptotic analysis. See, 1 by n is less than 1, equal to 1 minus 1 by n, equal to n power 1 by n. See, this is beautiful. If you look at this, see, this is so beautiful. What this is saying is that 1 is asymptotically equal to 1 minus 1 by n, is asymptotically equal to n power 1 by n. That means even 1 trillion power 1 by 1 trillion is a constant. And n power 1 by log n is in the same set. Sigma 1 by I squared is in the same set. It's just a constant. Sigma 1 by 2 power I is in the same set. Right? So similarly, you will be able to compare these functions. Okay, so let's see some of these. How do you show that 1 by n less than 1? The best way to solve these kinds of problems, right, is using limits. So try to use limits. Limit of 1 by n divided by 1 is 0. So which automatically means 1 by n is in small o of 1, right? You write it like this. Okay, so how do you show that n power 1 by log n is asymptotically equal to 1? So apply this, the first function divided by the second function. Second function is anyway 1. So you have n power 1 by log n. You should know some rules from log also. Log of AB is equal to log A plus log B. Log of A power B is equal to B log A, and n is equal to 2 power log n. See, some of these are very basic things, right? Base 2 here, base 2 here. So n can be written as 2 power log n. I mean, assume that whenever we write log in computer science, right? It's not base 10, it's not base E, it's base 2. In mathematics, when people write log, they usually mean log base E, log x base E. So this, in computer science, we write it as ln. Natural log is ln x, right? In computer science, whenever we write log, we mean log n base 2, because everything is powers of 2, 0, 1, right? And powers of 2. So when we don't write the base, assume that it is 2 everywhere, unless explicitly mentioned. In mathematics also uses base 10, but here we will not use base 10. We will not use E unless explicitly mentioned as a ln. In computer science, base is always 2. So this is 2 power log n base 2 whole power 1 by log n. This cancels out 2. Right? Okay, so let me complete one more slightly complicated version here, right? What do we have here? N power 1 by n is asymptotically equal to 1. So we have n power 1 by n. We can write this as e power ln of n power 1 by n. I mean, how can we write this? So can we write like this? This is equal to this.
Yes,
Why?
because the base of log is the same.
Exactly. E is equal, so A is equal to 2 power log A base 2. Is this correct?
Yes.
Similarly, a is equal to e power log a base e. That's what is written here. Log base e is ln, right? Okay, now what do? We take this outside. It's ln n divided by n. And we know a formula, right? Formula for e power x.
Expansion.
Let's use that Maclaurin series for e, right? If we use Maclaurin series for e power x, what do we get? 1 plus x power 1 divided by 1 factorial, x power 2 divided by 2 factorial, so on, where x is your this, ln n by n. Okay, then you can pull 1 outside. Then what do you get? You have divided by I factorial, right? You can consider this term is definitely less than or equal to this term, the numerator only, because you are dividing by I factorial, right? Hence, we write a less than or equal to and remove this positive denominator.
Actually, someone proposed one method I think is very powerful. You look at the power, right? It's the power goes to 0 when n equals to 0. When n goes to 0, right? Log n divided by n, log n decrease faster than n. So when n goes to infinity, log n over n will go to 0 quickly. So that's e to the power of 0.
E to the power of 0.
No, I mean, if you look at the e to the power of log n divided by n, right? Let's forget about the e. Let's just look at log n over n.
Right.
When n goes to infinity, this goes to 0.
True. You're right. I mean, we could apply the limits directly to that power, right?
But isn't ln of infinity is equal to infinity?
Yeah, but you use L'Hopital's rule and you get
Exactly.
Yeah.
And
So
Converges.
Exactly. So why didn't we apply that directly? Is like we had to use that L'Hopital's rule and all, right?
But we can't apply the L'Hopital's rule, right? Because like it's e to the power something. It's not fn divided by some gn function.
No.
Right.
That's fine. That's fine because you're applying n to here, so you can still apply the limits on this.
Yes, you can.
Right. So you can still apply the limits on this and use L'Hopital's rule and solve that problem.
Yeah. So the top becomes 1 over n. The bottom becomes 1. The 1 over n decreases quickly when n goes to infinity.
Right. So good. That is also a very nice method. But again, you need to use L'Hopital's rule and use the differential and everything, right? That definitely works. So here what we did is we took this and we wrote it as 1 by x, where x is n by ln n. Right? And what do you see here? This is a geometric series. The summation of this geometric series is upper bounded by this, right? 1 by x minus 1. And what happens to x? X goes to infinity. Then this is 0. So you get the same answer if you had chosen that other path also, right? You'll get the same thing, e power 0. Good. So this is one approach. As again, there are multiple ways to solve the same problem. And if you keep searching for different ideas, right, you get a wide variety of ideas. But very powerful method, as we have discussed today, is limits. So try to use limits heavily to solve the homework problems. And so learn these. I mean, we still have a couple of problems to cover, but just to give you a head start so that you can start on. Okay, so we will cover the other problems in the next session. Any questions, team?
Professor, excuse me. Is that possible that after this class, like after last